Go ahead.
So I'm Laura Grasso, and I'm the program delivery partner for First Lego League. And First Lego League is broken into 3 separate programs based on the ages of participants. So it starts with First Lego League Discover, which is for children from preschool age up to 1st grade. Then it moves on to First Lego League Explore, which covers children from about kindergarten to about 4th grade or about 10 years old. And then First Lego League Challenge, which is the largest of the programs. This covers children from about 3rd grade or about 9 years old, all the way up to 8th grade or 14 years old. So I run all 3 of these programs for the state of Arizona. And we have about, currently we have about 150 teams in the First Lego League Challenge portion of the program. The other 2 will start in the spring, but right now First Lego League Challenge is going on. It started in August and it will run through January. In a typical year, we usually have about 370 teams across Arizona. They're all around the state. This year, we're kind of building back up. Last year, it was a really small year, but this year, we're kind of moving our way back up to having more teams. The teams are returning. The teams are usually about 10 kids. And when I say teams, I'm referring to the First Lego League Challenge program. Usually a maximum of about 10 kids. Arizona has an average of about 6 kids per team. And what the kids do is there's different components to this competition. So they register their team with First, and they are mailed a Lego set, which we call the field set. And with that field set, they set it up on a huge table and they begin coding their robots. The robots that are used this year are Spike Prime. In the past, it was EV3. And I know for certain there has to be kids in this class that have taken this, that have participated in this program in the past. It's such a huge program. It's an international program, by the way. We are across the United States and into a whole bunch of different countries. Let me move on to the next slide here. So every year with First, there is a season theme. This year's happens to be First Forward, and it is heavily supported by Amazon and Qualcomm. And it's all about supply chain and the movement of goods in all various routes. Cargo Connect is that's the theme for First Lego League, all 3 of the programs that I cover. And then as you get into the older ages, high school, the FTC program, which is called First Tech Challenge, that is Freight Frenzy. And then into the First Robotics competition is Rapid React. So they're all covering supply chain, but they're a little bit different in their themes, just they get a little more sophisticated. For my purposes, I'm just going to be telling you about First Lego League today. So when the kids join a team, there's basically 4 main structures of what they're doing on the First Lego League program. The core values is kind of the fundamental how these teammates are engaging each other, how they interact, how they treat other teams, how their parents act at competitions. It's all about learning to be a professional and learning to be in competition with other teams, but also cooperate with them. So they kind of have these words that are the first code words, and it's cooperation. So you are in competition with other teams, but you need to cooperate together to advance your ideas and advance the program. And it's kind of the fundamental engineering core values almost, where you're in competition with other companies, but as a whole, the companies are working in cooperation in order to move the products forward, advance research, share ideas. And so core values is a huge important component that covers even when they're running their robots, when they're in the judging room, how they're behaving at tournaments. Are they being mature? Are they being good kids? Are they swearing at other kids? Are they being mean to their teammates if they make a mistake when they're running their robot? These are all things that are looked at when the kids are in the competition. And that is actually 1/3 of their score, is the referees and the judges reviewing how the kids are interacting with each other. Robot design. So this is, I'm going to show you a quick video. Actually, it probably doesn't even need sound, but I'm going to show you a quick video of some of the teams and what they have done this season so far. So the season started August 17th, and so everything was mailed out mid-August. So the kids not only put their Lego field sets together, but they also have programmed their robot to perform certain missions. And you'll see in this video coming up how intensely serious some of these teams are. There's one in particular in New Zealand. Their video wasn't that good, but they are always the ones that they have the robot coding down within just a couple weeks. They have the whole game, and they have all these crazy points. So as the robot moves around the field, let me show you the field. So these are the fields that the robots will be driving on, and the spike. These are little spike robots. There's 2 fields that are together, so each team would be at a table, and they set their spike robot down in the corner, kind of where that the quarter round is, where it says First Lego League Challenge. That's their home base, and there's a certain amount of points that they get for being able to fit into that black area next to that white circle. There's points if the robot comes back. I'm not an expert on these games. I'm mainly running the program, so I'm sure that there's people that have done this before that could give way more insight. But it's basically, it is a game. And in this, I don't know if you can see my mouse, but in this image here where the table is kind of close up, you can see a spike robot that someone put together. It's kind of in the midst of driving on the field. So each of these different Lego pieces are they're different missions. So let me swing over. I'm going to share my, let's see if I can show you. So this is one of the teams, and we actually don't even need sound. So basically, the kids are, am I sharing? Can you guys see that? I hope so. Ooh, let's do this one. Let's share this one. Okay, so just going back. So this is the robot that is, okay, perfect. I had to check the chat. So this is a robot that's been programmed, and they use scratch coding, but these spike robots can actually also be programmed with Python. My previous student worker, this was a really important component for him. He loved helping teams program their robots with Python. It does allow for a little more sophistication as the teams get older. You know, if they've been using scratch coding since they were 8 or 9 years old, or even earlier if they're using the We Do robots. But basically, if we go back, you can kind of, or even start, let's go back. So as the team is coding their robot, they're also building pieces onto the robot. So you can see that there's all these additional Lego pieces on the robot, the wheels, the little thing that's moving that knocked the semi-truck out of the holder. All these are components. This is all part of the robot design, which is another part of the judging that the judges are looking for, is how well did the kids build their robot? What are the components that they added onto the robot? There are some kids that they have these massive robots that are just enormous. So can they talk about the add-ons that they've done for the robot? Can they talk about their coding? So when the kids go in the judging room, they have to be able to talk about the code that they created for this robot and how it coordinates with the add-ons to the robot. One final bit of information. I know I'm running into time here, but my whole point in talking to you all is that there are a lot of teams that that have requested support. So a lot of times these are teams that are in community centers such as Boys and Girls Clubs, or it's just a STEM teacher that is running the team with the kids. And the teachers are often a little intimidated by programming the robots, talking about, let me share my screen again, talking about the coding with the kids, or trying to understand what the kids are doing, or how they should build onto the robot. So often we will have college kids that are mentors to the teams. And I've had many teams this year. I have a lot of new teachers that are completely overwhelmed, that are looking for team mentors. As you are older in college, the teachers really want your experience to be able to help the kids with the coding or the robot design, or another component of the competition that I didn't talk about was the innovation project, where the kids are solving a problem. There's a lot of different ways that you can be a part of these teams, the First LEGO League teams. You can either do it in person or virtual. We also rely on volunteers for our tournaments. In particular, we need judges and referees. We need referees for the robot game where the robot is driving. You would be calculating their points based on how well the robot performed the mission. The judges, the judging we would have either for robot design, which includes the robot, the add-ons to the robot and the coding that the kids have done, how well the robot was built, all the add-ons, how creative they were or unique, how well they solved their problems with the robot, and then the innovation project judges, which are hearing the project that the kids have put together. This year it's solving a problem in the supply chain. So that's a huge, broad topic that the kids would be researching this year. Team mentor, tournament judge, or referee. We also have a state championship here at ASU in January. In a typical year, we have 96 teams that come to the Memorial Union over 2 different days. And they come and they run their robots and they go talk to judges. So we are always looking for volunteers to help with the state championship. This is a great way, if you happen to live close to the Tempe campus, you just show up and you meet with the kids, or you just help around the tournament. The qualifying tournaments are all around Arizona. So we have some in Tucson, Flagstaff, Yuma, Sierra Vista. We have Phoenix, way north Phoenix up by Anthem, Scottsdale, East Mesa. They're all over this year, and they will always need judges, referees, and just general volunteers, if that's something that interests you. In particular, we have a scrimmage that's coming up with Si Se Puede, their STEM center, which is in Chandler. It's right over by Chandler High School. Si Se Puede used to have a facility down in Phoenix, and they have a whole bunch of different robotics programs there that even go beyond just the First LEGO League. These are into the high school students, the underwater robots. They have a whole bunch of different stuff. So they are actually having a training on Friday, September 17th from 9 a.m. to 2 p.m. And they are looking for just a few people, 2 or 3 people, to come and help the little kids on the teams kind of get started with their coding, how to understand maybe how to build their robots. It's a very fundamental, here's the robot, let's figure this out together kind of training. There is a stipend of $200 for anyone that is able to do that. Saturday, October 2nd, there is another position. He needs referees for a scrimmage. So you would be calculating the points as the robots are running. Again, he just needs a few people to be referees, and that there is a stipend of $200 for that as well. If any of this is interesting to you and you would like to know more or get involved, go ahead and send me an email at laura.grosso@asu.edu. So I'll leave that up there just for a second, just in case you want to write down the information. Did anyone have any questions? I can see the chat. So yeah, the STEAM Center just opened up. Austin, were you involved in FLL as a student? No? Oh, but you did mentor a team? Okay. It's very weird to be reading chat. So he said, Austin said yes, mentored a team, but did not participate. So, and really the mentorship can be it can be as easy as just sitting down with a virtual, that's okay. It's as easy as sitting down with the kids on Zoom and just helping them, taking a look at maybe they can share their coding with you and talk about what problems they're running into. The kids are not going to be able to do every mission on that field, especially these teams that want mentorship. They're going to be able to finish maybe one or two, maybe three, but the really good teams, maybe four, maybe five, but really no teams are coming in and wiping out every single mission. So you're helping them understand the missions, how they should build their robot, and just helping them kind of get on their feet. There are some students that love to meet with these teams in person, and I kind of leave that up to the mentor themselves, but there are some that want to meet with them in person and kind of get their hands on the robot and help them really start putting stuff together. So yeah, I knew there were people in here. And I'm sorry to be taking so long, but I knew there had to be people in this class that were, and yes, international students, absolutely. Absolutely. For the scrimmage positions, everyone is available to participate. Send me an email and I will forward it on to Alberto, who runs the Si Se Puede. So I think if that is it, I will let you guys get back to your class.
Thank you, Laura.
Absolutely.
You cannot hear anyone else clapping because everyone is muted.
That's okay. They're clapping in their heads. Thank you, guys.
But if you want to email me your slides.
Sure, absolutely. I'll send it to you.
Slides.
All right, well, have a good class.
Okay, thank you.
Bye.
Bye-bye. Hello, welcome everybody. I hope that was informative. And once again, I have extended the deadline for assignment 2 by 1 week. So please take a note. The other thing I want to tell you that I made a mistake in last class while working out the first problem. So what I want to do today is I want to go back and show you or kind of tell you what mistake I made, and then actually answer the question that someone raised about the forward kinematics. So this is the problem 1. And in this problem, I won't solve the complete problem, but I will show you the setup. So we have the first Revolute joint. Then we have the second Revolute joint. And this second Revolute joint is attached to a prismatic joint. So there is a prismatic joint here. And the issue with this prismatic joint, so this is R, and P. So what we did, we actually showed that this is similar to one of the problems in assignment 2, but this is the problem that I worked out in the last class. So quick note, error in problem 1 last class. So I just want to show you what error I made. So we set up the coordinate system. So this is x naught, this is y naught, this is z naught. Then we have z1, y1, x1. So z1, y1, x1. And then we have x2, z2, and y2. And last but not least, we have the end effector, and the end effector has x3, z3, and y3. So we have these coordinate systems. Now, the important issue that to be noted is the DH parameter rules, or the 4 rules, are not satisfied. So we actually have exception to rule. And what we did for that is we actually translated the frame number 2. So we translated this frame. So we translated this frame over here. So basically, we translated x2, z2, and y2. And now what happens is, the first homogeneous transformation matrix, there is no change. So this was correct. 0h1. 0h1 was cosine theta 1, 0, sine theta 1, 0, sine theta 1, 0, minus cosine theta 1, 0, 0, 1, 0, A1, 0, 0, 0, 1. The second homogeneous transformation, since we have transferred the frame, the distance between frame number 1 and frame number 2 is 0. So your second homogeneous transformation is something like this. So, and I derived this in last class. So cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0. Now, the problem occurs when we have 2H3. Please note, in 2H3, there is no rotation matrix. So basically, there is no rotation. So we just have a prismatic joint 0, 0, 0, 1. Now, the key question here is what would be at this location, what would be at this location, and what would be at this location. Now, in last class, I made a mistake. I said, and I will tell you what mistake I made. I said here it's going to be A2. So here is going to be A2 plus D2 and maybe a sine theta 2. That is incorrect. So this is wrong. And I'll tell you the reason why this is wrong. So if you want to see the rotation, theta 2 is taken care by this matrix. the rotation is taken care by this matrix. So what I want at this point, I want the distance between frame 2 and frame 3 along x2, y2, and z2. So if you look at the kinematic diagram, if you look at the structure, this distance is A2. And this distance is D3. Please note D3 is going to change. A2 is constant. But I want you to look at this figure that I'm going to draw on the side. And that figure is something like this. I want you to look at this coordinate system. This coordinate system is x2. Sorry, this is z2. Z2, Z2, then this is X2, and this is Y2. And basically they coincide on the coordinate system, which is Y1, X1, and Z1. Now look at the last coordinate end effector frame. So end effector frame is X3, Z3, and Y3. So if you were to look at this distance from this frame all the way to this frame, this distance is just A2 plus D3 along Z2. And this is very important. This distance is A2 plus Z3 along A2 plus D3 along Z2. So here you are going to have 0. Here you are going to have 0. And here you are going to have A2 plus D3. So if you recollect, in the last class, I made a mistake. And in the MATLAB code, we were getting some weird results. So what I want to do here is go back to the MATLAB script and show you where it needs to be corrected. And then I would try to explain the results. Before I start sharing my MATLAB screen, any questions on this formulation? 0H1, everyone okay with 0H1? 1H2, that is correct, that we solved in last class. Please note, you have zeros on the fourth column because the frames are superimposed. Frame number 2 is translated back onto frame number 1. Yes, H12 takes care of rotation because if you now want to think about it, so if you look at this problem, H12 is taking care of the relative rotation between frame number 2 and frame number 1. Now, yeah, I understand. So if you look at 2H3, what by definition, this is the distance between frame 2 and frame 3 along X2, Y2, and Z2. So I want you to pay attention once again to this diagram, which is over here. This is the transferred frame, translated frame 2. And why did we translate this frame? We translated this frame because the DH coordinate parameters, the 4 rules were not satisfied. Because if you look at the original X2 was perpendicular to Z2, but it was not intersecting Z1. So I'm going to show you what I mean by that. If you look at original X2, that original X2, this original X2 is intersecting with Z2. It's intersecting with Z2, but it is not intersecting with Z1. H12, H12. Yeah, because now we have translated frame 2 onto frame 1. We have translated frame 2 onto frame 1, which means they are on top of each other. So there is a relative rotation. There is no relative there is a relative rotation, but there is no relative translation. That's why you have 0, 0, 0, and 1. The last part is when we do this transformation, please understand that D3 plus A2, that distance is along Z2, but Z2 is actually fixed to this link, and that link is going to rotate. So essentially, what I'm trying to say here, and this is very important, there is no relative rotation between frame 3 and frame 2. Once again, there is no relative rotation between frame 3 and frame 2, translated frame 2. That's why you do not have any rotation matrix, but you have the translation. Any other questions here? Did I answer this correctly? Any questions? I'm looking at the chat window, and I'm going to share my MATLAB screen so you will see the difference. So now I'm going to show you MATLAB. So I hope you can see my MATLAB screen. So this is the exact same code that we programmed in last class. Theta 1 is the first angle, theta 2 is the second angle, A1 is fixed distance, A2 and D3, H01, H12. The only difference here that I had made a mistake here. So I want you to make this correction, and I'm gonna copy and paste that in the chat window. So if you want to make that correction to your code, you can do that. Actually, let me type the whole code. This code is also uploaded on the canvas. So you are welcome to copy and paste this code in your MATLAB and then run this code. And once you evaluate selection, you will see now you would get a meaningful result. So you would see cosine theta 1 multiplied by cosine theta 2, A2 plus D3, cosine theta 2, sine theta 1, A2 plus D3, and A1 plus sine theta 2, A2 plus D3. Everyone got this code working? Okay. All right. Now let me explain to you physically what happens from geometry point of view. So what is happening is, if you look at this problem, we have two angles. We have a theta 1 here, and we have a theta 2 here. So we have theta 1 and we have theta 2. So we have theta 1 and we have theta 2. Now for a second, I want you to consider that theta 1 is 0 and we have a non-zero theta 2. So if we have a non-zero theta 2, what that means is I have, so theta 1 is 0. So theta 1 is 0, but I have a non-zero theta 2. So this is my theta 2. And this is my end effector. So this is the end effector. And this distance is effectively A2 plus D3. This distance is A2 plus D3. So if you were to look at, and again, you have your prismatic joint here. If you look at the components, this component is going to be A2 plus D3 cosine theta 2. And this component is going to be A2 plus D3 sine theta 2. Are you with me so far? Now, let's look at the base frame, the very first frame that is over here. So this is the zeroth frame. So this is my Z0, this is my X0, this is my Y0. So at this point, what and this distance is actually A1. So what is the distance? What is the distance between the end effector and the base or the inertial frame along Z0? That distance is nothing but A1 plus A2 plus D3 sine theta 2. And I want you to take a minute and see if that is the same answer we got on the homogeneous transformation 0H3. So this is 4, 1, 2, 3. So I want you to check that you got this answer at this location. You got this answer. So you would get this answer over here. Now, assuming there is no rotation, assuming the value of theta 1 is 0, assuming the value of theta Z plus D Okay, can you hear me? Awesome. Yeah, I don't think it's the issue with Wi-Fi. I just checked my speed. My Wi-Fi speed is good. It's just the issue with the Zoom data center, unfortunately. So assume theta 1 is equal to 0. If your theta 1 is going to be 0, you are going to have this term over here. And I want you to check your homogeneous transformation matrix that we calculated. And you will realize that the first term there is cosine theta 1, cosine theta 2, A2 plus D3. So if your cosine theta 1 is 0, your cosine theta 1 is going to be 1, and you are going to have 0 over here, because sine theta 1 is going to be 0, so sine theta 1 is going to be 0, so you are going to have 0. Now I want you to just try to visualize, try to see this in a top view. So if you look at the same figure in the top view, I want you to look at the same figure in the top view and assume that there is a non-zero theta 1. Assume that there is non-zero theta 1. So in the top view, you're going to see the projection. This projection is going to look like A2 plus D3 cosine theta 2. And now you will notice that this will have its sine and cosine component. So this is going to be A2 plus D3 cosine theta 2 cosine theta 1, and this distance is going to be A2 plus D3 cosine theta 2 sine theta 1. Okay, can you hear me? Okay, so this is what the homogeneous transformation is going to look like. So if I were to rewrite the last column of homogeneous transformation, you will notice this is going to look like cosine theta 1 cosine theta 2 A2 plus D3. Then this is going to look like sine theta 1 cosine theta 2 A2 plus D3. And it's going to look like A1 plus sine theta 2 A2 plus D3. And clearly there will be 1. This is the fourth column. And so this is the fourth column, all rows. There is no time in you mean the multiplication? Okay. So, and I would like you to look at the MATLAB code that we did. Just look at the MATLAB code and see this is what you get. Any questions? What I want to do is I want to solve one more problem. And please note these solutions are already uploaded onto Canvas. So just in case if you want to refer back, you can just still go back to Canvas, and I have uploaded the notes with these solutions. So let me take one more problem. So in this particular problem, we have a revolute joint. This revolute joint is attached to a prismatic joint. This prismatic joint is attached to another revolute joint. And this is how the revolute joint looks like. So if you think about it, this is the first revolute joint R. This is the prismatic joint. Then this is the Revolute joint. So you have the Revolute joint. Yeah, I'll answer that question in just a second. Let me try to finish this problem real quick. So now, first and foremost, this is the end effector, and we have to solve the forward kinematics problem. So in the forward kinematics problem, as usual, I have to set up the coordinate system x0, z0, y0. Then I have z1. I have z1. Then x1. So z1, this is actually y1. Y1 and x1. And then I have again z2, then I'm gonna have x2, and I'm gonna have y2, and last but not least, I'm gonna have x3, y3, and I'm gonna have z3. So before I proceed further, I just want to ask you that just make sure that this coordinate system is satisfying the 4 rules. This is theta1. Then I'm gonna call this theta3. And then I'm gonna have one distance, which is d2. And I'm gonna call this a1. And I'm gonna call this distance a3. So y2, so first and foremost, okay, so I'll answer all the questions step by step. First question is, if you look at the rules, the rule is we want to make sure that x2 is perpendicular to z2 and x2 is perpendicular to z1. And so what that means is once we set up z2 and once we set up x2, the triad should be completed. So curl your fingers, right hand coordinate system, and you will see that if you have z2, which is coming out along the joint axis, x2, if that is going up, clearly your y is going to go towards the left hand side. It's doesn't matter. Your x2 can go up or it can go down. It doesn't matter. So depending upon, so there is no harm in pointing x2 down, then your y2 will go towards right. But yeah, z2 can also go. Z2 can also go other way. It can go out or it can go in, as long as it's in the joint axis or articulation axis. Okay, the next thing I want to answer here is, this is the convention. This is the zeroth frame. So zeroth frame has the articulation angle theta1. This is the first frame. Frame number 1 has articulation angle d2. And this is frame 2 that has articulation angle theta3. And this is frame 3. So please note, frame number 0 has articulation theta 1. Frame number 1 has articulation associated with 2. And frame number 2 has articulation associated with 3. Articulation could be rotary articulation, which means it would be theta, or it could be reciprocating articulation, so that could be D. That to answer Adriana's question. So it should be, that's why we are saying it is theta 3. That's just the convention, but you can use other convention, that's totally fine. Now with this, what we want to do is, we want to first set up the coordinate system that we have and write down the first rotation matrix, 0R1. 0R1 is cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, multiplied by the projection matrix. And this is the projection of x1, y1, z1 onto x0, y0, z0. And see the projection, that is going to be x1 is aligned with y0. x1 is aligned with y0. y1 is aligned with z0. And z1 is aligned with x0. So this 0R1, this matrix, is going to be minus sine theta 1. Once you perform the multiplication, 0, cosine theta 1, cosine theta 1, 0, sine theta 1, 0, 1, 0. That allows us to find the homogeneous transformation matrix, minus sine theta 1, 0, cosine theta 1, cosine theta 1, 0, sine theta 1, 0, 1, 0, 0, 0, 1. And I'm going to have, so this is going to be 0, 0, A1, 1. Any questions here on this homogeneous transformation matrix? First homogeneous transformation. The next is 1R2. And in 1R2, it's a prismatic joint. So yeah, that's right. So the rotation of frame number 2 with respect to frame number 1. Since it's a prismatic joint, no rotation. 0, 0, 1. But nevertheless, don't forget the projection matrix. x2, y2, z2, x1, y1, z1. This is going to be 0, 0. See, it's minus 1, 1, 0, 0, 0, minus 1, 0. So when you perform the multiplication, what you get, and I'm going to rewrite the homogeneous transformation here, 1H2 is going to be 0, 1, 0, 0, 0, 0, minus 1, 0, minus 1, 0, 0, 0, and you'll have 0, 0, D2, 1. So this is how the homogeneous transformation for the second matrix or 1, 2 gonna look like. Now here comes the problem that we want to solve. So we have x3, and I want you to pay attention to x3 for a minute. x3. x3 is perpendicular to z3. x3 is perpendicular to z2. So x3 is perpendicular to z3, x3 is perpendicular to z3, but x3 is not intersecting z2. So please note, x3 is perpendicular to z3 and z2, but does not intersect z2. So in other words, the one rule is not satisfied. So what I need to do is I need to translate this frame. So I need to translate this frame from 3 onto 2. So what I'm going to do is I'm going to construct or translate this frame. This is going to be x3, y3, and z3. So, but then you have an end effector. So clearly, once you do this translation, we need to have y not to flip x3 and y3. If we flip x3 and y3, let me see, x3. Yeah, actually you can do that. You can certainly do that. But let me take an exception here and solve this problem. So in case if you have similar question somewhere else, but that's totally fine. You can actually change x3 because it's not the joint articulation, so it doesn't matter, but then you will have a projection matrix. So you will have to deal with the projection matrix. Let me solve this way, and then I will try to solve it with flipped axis as well. So that's totally cool. That's fine. So what I want to do here is, so first and foremost, I would like to translate x3, z3, and y3 onto x2, y2, and z2. And once this translation is done, I can write down 2 R3. So 2 R3. 2 R3 cosine theta 3 minus sine theta 3, 0, sine theta 3 cosine theta 3, 0, 0, 0, 1. Multiplied by the projection matrix, and that projection matrix is x3, y3, z3, x2, y2, z2, and as you can see, this is 1, 0, 0, 0, 1, 0, 0, 0, 1. So I would go ahead and write down 2h3 directly here. So 2h3 is going to be something like cosine theta 3 minus sine theta 3 cosine theta 3, 0, 0, 1, 0, 0, 0, 0, 0. And please note, since we translated the frame, it's going to be 0, 0, 0, 1 because the frame is translated. Now, we need to specify some additional frame just for the end effector. And I'm going to call this sort of end effector frame. So, and I'm going to call this maybe x4, z4, and y4. And the only reason I'm doing this is because we translated the frame. And I have x4, y4, and z4. And what I would do now is actually, this becomes an interesting problem here. I would write down 3R4. And this 3R4 is going to look like 0, 1, 0, 0, 0, 1. And then it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And now when I do 3H4, I have 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, minus A3, 0, and 1. Yeah, I will do that in just a second. I will do that in just a second. But let me finish this problem. And to find out the total homogeneous transformation, you will have 0H1, 1H2, 2H3, and 3H4. And you can do this, and that is because it's in the negative direction. So if you look at this direction, Y3 is negative in the direction of A3. Yes, so I'm gonna do one more thing here. Just bear with me for a second. Yeah. So I just added frame 4 just to show you that if you were to translate, if you land up something like the problem, something like this, wherein you have 4 rules not satisfied, then you can translate. Now, how would you solve the same problem in a slightly different fashion? So let me try to work out the same problem in a slightly different fashion. So think about it, that we have this joint, and clearly your argument is right, that why do we need to follow the frame coordinate system when there is no articulation? That's totally fine. The only problem is when we are going to set up the DH parameters and DH parameter tables, not now, a little bit later, where what we do is we set up a table and then try to solve the problem using a tabular approach. We have to make sure that these 4 rules are satisfied all the time. So let me explain this problem once again in a slightly different fashion. So bear with me for a second. So this is X2, this is Z2, and this is Y2. Now, if you look at in the earlier problem, when I set up the coordinate system, what I did, I said that my coordinate system on the end actuator or end effector here, I want it to be parallel or in the same direction as the old coordinate frame. Now, what I want to do is, but then if I were to construct the coordinate frame just like the old coordinate frame, I can totally see that my X3 is not going to satisfy. Yeah, just hold on a second. So so let me show you what I did. X3, Y3, Z3. This is the coordinate frame that I used. And the reason I use this coordinate because since it's the end effector, I just tried to duplicate the coordinate frame that was behind or before end effector. Now, but when I use this coordinate frame, what happens is my X3 is perpendicular to Z3, my X3 is perpendicular to Z2, but my X3 is not intersecting with Z2. Everyone understood this part? Kaiji? So the rule is, if you have a rotary joint or if you have a prismatic joint, Z-axis has to go to the rotary joint or the prismatic joint. Since end effector does not have a prismatic joint or a rotary joint, it doesn't have to follow that convention. But in the past problems that we have worked out, it makes easier. The projection matrix becomes identity if my x3 is aligned with x2, my y3 is aligned with y2, and my z3 is aligned with z2. But in this case, once again, I repeat, if my x3 is aligned with x2, if my z3 is aligned with z2, and if my y3 is aligned with y2, my projection matrix becomes identity. Okay. But in this particular problem, the issue is if I choose this particular configuration, my rules are not getting satisfied. So what I'm going to do is I'm going to make a slight change, and that will make things very clear. So I'm going to assume my Z3, which is in the same direction as Z2, but just I would use my X2, something like this. I would use my X2, something like this. And once I have my Z3, once I have my X2, I'm gonna have my, X3. So this is going to be my X3. It's going to be my X3. And this is going to be my Y3. And now you don't need to translate anything, because if you were to see that all the four rules are satisfied. So if I were to construct the rotation matrix with this guy, I'm going to have 2 R3 cosine theta 3 minus sine theta 3 sine theta 3 cosine theta 3 0 0 0 0 1. Then I'm going to have my projection matrix, and this is going to be x3 y3 z3 x2 y2 z2. Look at x3. X3 is in the same direction as y2. Y3 is opposite of x2, and z3 is in the same direction as z2. So first row, first column, minus sine theta 3. First row, second column, minus cosine theta 3. First row, third column, 0. First row, first column, cosine theta 3. So first row, first column. Then you would have second row, first row, first column, first row, second column, first row, third column, first row, second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. So now this is your 2R3, and then 2H3. So 2H3 this is going to be minus sine theta 3 minus cosine theta 3 cosine theta 3 minus sine theta 3 0 0 0 0 1 0 0 0 1. And now comes the fun part. The distance between these two, this frame and this frame, is A3. This distance is A3. And this distance has to be valid all the time. This distance has to be valid all the time. So this is going to be, and pay attention here, this is going to be the projection along x2, y2, z2. So projection along x2 is going to be a3 sine theta 3, a3 cosine theta 3. But please note, y2 is in the opposite direction. So y2 is going like this. So this has to have a negative sign. So this would be minus a3 cosine theta 3. And around z, there is nothing. So this becomes 0. So z3 becomes 0. So what you can do is you can 0h3 can be found out at 0h1, 1h2, and 2h3. So this is how you can solve the problem. Either you can translate the frame and work out the problem, or you can just go ahead and use the matrices, the coordinate system in such a way that they follow all the 4 rules. And I'm emphasizing on these rules a little bit because please note, after next class, we are going to use something called as the DH parameters. Minus A3. No, in this case, it won't be. I tell you the reason why. Because we are not translating the matrix, translating the frame here. So to answer Viraj's question, this 2H3 matrix is correct because in this particular problem, we are not translating the frame. So that is, so this matrix translated, there is no translation of the frame. We haven't added Z4, X4, and Y4. Does that make sense, Viraj? Okay, then I suggest what you do is you work out the problem both ways and then let me know if there is an error or there is a mistake. And again, it totally depends, depending upon the problem statement. You can choose the right coordinate system, and if the 4 rules are not satisfied, then you cannot, if the rules are not satisfied, the DH parameter technique cannot be used. So you need to do something to make sure that those 4 rules are satisfied. And in case if you look at the notes, I have actually added a verification section in the last problem. So page number 5 of the notes that I uploaded, there is a verification that actually shows you that your answer is going to be the same. So you are welcome to take a look at notes, and I have worked out this problem in the notes. That's it for today, and have a great weekend, and I will see you on Tuesday. It does not matter which orientation the rotary joint is drawn, as long as it represents the robot and the z-axis is passing through the joint of articulation. Any other questions? Okay, change the direction of Z2. In this problem, psi is in this problem, you want me to. So I thought that's what I did here, no? I changed the, okay. So if you change the direction of Z3, so it will look something like this. So let me ask you this, in what direction you want your Z3 to be? Opposite direction of Z3. Okay, that's totally fine. So let's see that Z3 is here. So I'm gonna have my Z3 like this. Is this good? Okay. Now, if my Z3 is like this, what I'm gonna do is, can I assume my X2 to be something like this? Or X3 to be something like this? And now I want you to curl your right hand fingers and tell me if your X3 and if your Z3, what direction your Y3 is going to be. I think Y3 would be like this. Just see right hand coordinate system and make sure that X3 is the thumb. X3 is the thumb. Your Z is the middle finger, and first finger is Y. Are you with me so far? Fine. Okay. So now what I want to do here is my rotation matrix is not going to change. So this guy is going to remain the same. So this guy will be same. Only my projection matrix is going to change. And what would be my new projection matrix? I'm going to write this down here. So check this out. X3 is in the minus direction of Y2, minus 1. Then I have Y3, which is in the direction of minus X2. And my Z3 is in the direction of minus Z2. Can we put Y3 to the top? Y3 has to be down because your right hand coordinate system, your thumb is going to be your X. Your middle finger is going to be your Z. Your first finger has to be your Y. You see what I'm saying, Kaiji? So I will write this again. This is your thumb. This is your middle finger. So tell me, where is your first finger? Oh, this is the ring finger. Yeah, middle finger, not the ring finger. So this is the first finger. So your position matrix would be like this. Now what's going to happen is, when you do the homogeneous transformation, you will have changes something like this. You are going to have A3 cosine theta 3, A3 sine theta 3. This would be A3 sine theta 3. A3 sine theta 3. And you are going to have minus A3 cosine theta 3, 0 and 1. And this is going to be your R2, 3. So R2, 3 comes from here. In 2R3 will not be my, okay, 2R3, let me check real quick. So this is X3, Y3, Z3. Its projection on X2, Y2, Z2. X3 is in the direction of minus Y2, Y3 is in the direction of minus X2, and Z3 is in the direction of minus 1 on the top left. So this frame is for this guy. No, this matrix is going to remain the same. This matrix will be same. This matrix is going to be the same. Because that's not going to change. Yeah, let me unmute you for a second. Yeah, Sai, you're unmuted.
So the matrix that remain the same, will the minus one not, sorry, will the one not be minus one?
So I'm not sure which matrix you're talking about. Are you talking about
the matrix which you say it remains the same, since Z is anti-parallel to Z3 is anti-parallel to Z2, will one be not be minus one?
no? One will never be minus one.
Okay,
So
if it is okay, whether it is parallel or anti-parallel, it will be one.
Yeah. So basically, so what it's not, if you mean to say something like this, if you mean to say something, if you have your Z2 like this, is that what you mean? Please note your theta 3 is around Z2. If your Z2 is like this, okay, then for theta to be positive, you're assuming this to be rotation. Here, you're assuming your rotation to be like this. You see what I'm saying? Sai, do you understand this? Okay, so now the next question is from okay, thank you, Vijay. Viraj. Okay, what was it? A sine theta 3 into H3. A sine theta 3 into H3. A sine. Okay, so if you look at A sine theta 3, so basically this is the angle, right? So if you look at the projection, so you are going to have a cosine and a sine. So that's why in 2H3, you have this component, which is A3 sine theta 3, and you're going to have this component, which is A3 cosine theta 3. Okay, I have another class in 5 minutes. So if first join from ground. Yes. So basically you will have to start from the inertial coordinate frame or the base coordinate frame to solve the problem. And again, if you have any questions, I would have office hours today starting 7:30 via Zoom. Same link. You can just log into the link, and I will try to explain the problems, or if you have questions, I'll be happy to help you out. So 7:30, same Zoom link. Okay, I'm gonna stop recording. Yeah, it's Borna. His email is on the canvas, and he actually sent you multiple emails regarding the part collection and all, so you can reply to that email and you can set up the time with him. But if you want to send me an email, I would be happy to reply to that email and copy Borna on that email. Any other questions? Okay, I'm going to stop recording.